Hello, welcome to our introductory video tutorial for SES CorrCAD, which is a cathodic protection system design and corrosion evaluation module. Let's begin by launching the CorrCAD program from the SES software folder. The application loads on the main screen. First, we will open a new page from the File menu. Next, choose Save or Save As, again from the File menu, to save your project in the preferred location. It is recommended that you save your file frequently while designing your model. Next, from the Options menu, you will select your unit system, either imperial or metric. Then, from the Polyline tab, we will click the Add New Polyline button. And next we enter the polyline's coordinates. As with mols and hyphae, a positive z-coordinate means that the object is in the ground, whereas a negative z-coordinate indicates that the object is above ground. You can choose the number of segments in order to break the polyline between 2 points. You also have the option of drawing a polyline using the pencil icon. Any necessary changes can be made using the Coordinate button. There are other options to create a polyline, such as importing a mols or hyphae input file that was prepared in CorrCAD. You can also import or copy-paste from an Excel file, or import a Google Earth KML file. We will delete this polyline as it was just for demonstration. The next step is the cross-section panel. Add a new cross-section and press the Define button. Here you can choose the component type, either from Database or Template. Then you may enter the data manually or use the Import Conductor button near the top of this screen to access SES Library. Within SES Library, there are several categories for the user to choose from. When you are finished entering the data, press the Create Component button near the bottom of the screen. Next, you define the horizontal and vertical offset of the cross-section. As with Treeline, a negative value for the z-coordinate means the component is in the ground, whereas a positive value for the z-coordinate means it is above the ground. Users have the option of changing the color of the cross-section as it is displayed on their screen. You may also change the name of your cross-section. The same can also be done for polylines. Next, you will assign the cross-section you've just defined to polyline segments. The same task can also be accomplished via the cross-section icon in the toolbar menu. Here you will select the beginning and the end of the desired segments. The next step is to add entities. Typically, you would have previously defined an anode bed in CorrCAD. Now, we will import or link to that anode bed from that pre-existing mols file. Next, we will specify the location of that entity in your model, which here it is located at both extremities of the polyline and also directly in the middle. In other words, at every 5-kilometer interval to install an anode bed. The location of entities can also be specified using the Entity icon from the toolbar menu and clicking on the desired locations to place your anode bed. The next step is to define the energizations. For this example, that is a cathodic protection rectifier current. Here we choose current as our energization type and apply a negative 3.5 ampere to the pipe, in other words the cathode, and a positive 3.5 ampere to the anode. Energizations can be added through the coordinate window for both polylines and entities. In order to review the network which we have just designed, we can open it in CorrCAD by clicking on the corresponding icon. The next step is to define the soil structure. Note that presently, CorrCAD only supports one soil model. Here we are using a previously defined file. Alternatively, we could have clicked the middle button to access the soil window to define the soil model manually. By hovering over the middle button, the tooltip will show information about the soil structure. The next step is to define observation points. This can be done either via the Entity tab by clicking the Adding Entity button, or alternatively, you can simply right-click on the polyline, and then from the pop-up menu, select Tools and then Polyline Operations. The Polyline Operation Tool dialog box will appear. Here you can rename the observation point and enter values related to its depth and also its spacing. The next step, if you would like to account for the polarization, is to define the galvanic series and the polarization curves. For the native or galvanic potential, we select a mild steel option for our pipeline. Click OK, and then define your curve. You may select from 4 curve options. Here we will choose the Butler-Vollmer curve. Next, we will use the parameters previously defined in SCS Curve Fit. Select Specify to access SCS Curve Fit. If you don't assign the galvanic series to your polyline, you will notice that the Compute with Polarization option is not available. We can still do the computations, but without polarization. Here we will assign the polarization to the pipeline, and then compute with polarization. As we can see, the pipeline overpotential is below the design objective of negative 0.85 volts. The pipe is therefore considered to be well protected from the risk of corrosion. The design was successful. On the left, the program reports overpotential and leakage current density. You can select objects to be plotted, iteration numbers, and the chart type. You can export the values to Excel by clicking the Export to File button. Thank you for watching. If you have any questions, please do not hesitate to contact us.